last class we started looking at how we go about doing static analysis, what are the rules, assumptions that we are going to make when we apply the principles of statics to the human body. So, today we will start with looking at doing some static analysis on the upper limb, on the arms. Okay. So, we will start off with first looking at some of the major muscles, because they are going to be the actuators. So, in your static analysis, as we mentioned, we will typically take a muscle. Our objective would be when the limb is subjected to some external loads, known body segment parameters, namely masses of the limbs, locations of CG, etc. We will then and also the muscle, what muscle would be acting on that limb. We would then try to find out what kind of force does the muscle have to apply in order to sustain the external loads that we are looking at, and what would be the forces that are generated, the reaction forces generated at the joints when such a load is being sustained. So, that is our objective. So, some of the muscles of the upper limb that or the upper body, if you look at it, you have, what view is this? The first one, this where you see the latissimus dorsi. Can you figure out what view? This is the posterior view. Remember, you can see the posterior view. So, this is the posterior view. So, the latissimus dorsi is one of the muscles that inserts into the humerus. So, the humerus is the upper arm, and the lower arm you have the radius and the ulna. So, you have, so if you look at the muscle and you know that it can only apply tension, you can kind of figure out what sort of motions it is going to influence. So, if this muscle contracts, what is the effect do you think it is going to have on the humerus? So, it is going to exert, so it is an adductor at the based on the view from the transverse plane. Okay. So, if it is on the inside, if it is inserted on the inside and it pulls, then it is going to cause medial rotation. If it is inserted on the outside, on the lateral side, and it pulls, it is going to cause external rotation. So, you can figure out from the way the muscle, knowing the insertions, the origin and the insertion, you can figure out how it is going to affect the limb to which the muscle is attached. Then this view, which view is this? This is your anterior view. You can see that you have the pectoralis, which is the chest muscles, which go from the, and then this is an important muscle that we will be looking at, and this is called the deltoid. So, the deltoid muscle, can you guess what movement it would affect at the shoulder? Okay. This muscle here, the deltoid, that is actually, there are three portions of the deltoid muscle. The one in the middle affects abduction. So, it will cause shoulder abduction. This again is a posterior view, and for the forearm, okay, you have the triceps, which are the elbow extensors. So, they cause extension of the elbow, the triceps muscle. And then in the anterior view, you actually have 3 muscles which are considered elbow flexors. So, this biceps, the brachialis and the brachioradialis are all elbow flexors. If your forearm is supinated, like in your anatomical position, then your primary elbow flexor is your biceps muscle. Okay. In most other orientations, the brachialis actually flexus is the primary elbow flexor, but if the forearm is supinated, then the biceps. So, that is why if you are working the biceps, you are always carrying a weight like this and working the biceps. Okay. If you do this, you are not working the biceps primarily. Yeah. So, or you know, when they do pull-ups, then again it is your biceps which are your biceps brachii which are your primary elbow flexors. So, the full name is biceps brachii. Biceps just means the muscle has 2 heads. It inserts, it joins into one tendon, but where it originates, it has 2 heads which insert into different places. Triceps again has 3 heads. Here you can only see 2 because one head is below, it is a deeper muscle. Okay. Then the pronator here is the muscle that causes this pronation. You can see if it pulls on the radius, you saw how it pivots about the ulna. So, this is what causes that rotation about that, the pronator teres. So, this is just some of the basic musculature that you may encounter when you are dealing with analysis of the upper. Now, let us go ahead with doing a static analysis of the elbow. So, what are the assumptions we are going to make? It is always important to the assumptions. So, actually if you look at elbow flexion here, you have the triceps here. So, the biceps are the agonist. Okay, they are the ones you have an external load that is trying to extend the elbow. So, if you want to hold it in the flexed position, your biceps are your agonists and the triceps had to happen. So, in most cases we will only look at the agonist muscle. See, we want to rest, okay, we will do a planar analysis in the sagittal plane. Okay, we are only looking at, so we are assuming that the elbow is essentially a hinge. Okay, we are looking at the elbow as a hinge joint which causes rotation in the sagittal plane. So, we are doing a planar analysis and we are assuming that elbow does not change. Okay, so, we know a single position, but we are assuming that it is a hinge joint. So, it is like a pin. Oops. Okay. So, if you look at the free body, so in this case because it is in the supinated position, we assume that, so let us forget about the triceps. For the analysis purpose, we assume that only one muscle is acting and we assume that that muscle is the biceps. So, we are neglecting the effect of the other muscles and also the ligaments, all the other structures. And we assume in this case that, say, the line of action of the muscle is known, and in this case let us assume that the muscle pulls, analyzing where the elbow is in 90 degrees flexion, and at this instance I am saying the muscle is perpendicular to the forearm. The muscle action is perpendicular to the forearm. So, if I draw this, so in this I have, if I isolate this, I have a pin joint. So, I have a Jx and a Jy which will act at that joint. I have a load WL of the forearm that I assume acts, I know that distance because that is from the anthropometric data. I know that it acts, and in this case we can assume that the forearm is uniform, and so we can middle of the length of the arm or some other known distance. And then I am making the assumption that I know that the muscle acts at a particular distance. So, let us say, so this is my elbow E, this is my point of muscle attachment. So, I know this distance, I know this distance, let me call it A, call this B, and I know where the load acts, let me call that C. So, from the elbow these are my distances. Okay. So, now I basically, how many unknowns do I have in this free body diagram? I have 3 unknowns, right. So, I am assuming a particular direction for Fm. So, only Fm, Jx and Jy. So, now I just apply the equations of static equilibrium, which would be sigma f equal to 0, which basically gives me 2 equations, sigma fx equal to 0, sigma fy equal to 0, and then sigma m equal to 0. So, I can take moments about the elbow. So, if I take moments about the elbow, Jx and Jy are eliminated. So, I have only one unknown. So, if I let us counterclockwise is positive. So, I have Fm A minus Wa into B minus Wl into C equal to 0. And from this, from sigma fx equal to 0, I get what is the value of Jx? Jx is 0 in this case, because there are no external loads acting along the longitudinal axis of the forearm. And then of course, I can find, so I can find Fm from the first one. And Jy will then be equal to Wa plus Wl minus Fm. So, let me now give you some values and I want you to quickly calculate. So, let us say the weight of the arm is 20 newtons, which is about 2 kgs. Weight of your forearm is about 2 kgs, 20 newtons. The weight of the load that you are carrying is, so you are carrying an 8 kg, so about 80 newtons, okay. And I will give you A equal to 4 centimeter, B equal to 15 centimeter and C equal to 35 centimeters. Can you quickly calculate and tell me what are the values of Fm, Jx and Jy? Next few classes, please make sure you bring your calculators, because we will be solving problems. Anybody? $75 newtons. Jx is 0, we found that, and Jy is minus 675. Minus 675 newtons. That means it is acting in the opposite direction. Okay. So, if you see here, the muscle force that is developed is almost 10 times the load that is being carried. Okay. So, and that is because of the small moment arm at which the muscle acts. So, the muscle is capable of developing this large force because in the body the moment arms are generally pretty small. So, the force capability of the muscles is pretty high, and what you lose in terms of having to apply a greater force in terms of the speed. So, because still acts here, right, your external load moves through, can move faster. So, that is the compromise that is made in the body. You have to exert large, move faster. Okay. So, and what kind of a lever would this be? Here if you look at it, this is essentially a lever. You have the fulcrum at the elbow, yeah, you have the fulcrum at the elbow, you have the effort applied, and this is your load. Okay. So, this is a class 3 lever. In the body. Now, this is at 90 degrees of flexion, right. So, we said okay, to support the load, if I am holding the load in this manner with my elbow flexed 90 degrees, this is the even the joints you can see experience pretty high loads. Okay. So, this is that is equivalent to a 67 kg load at that joint. So, that is so our body is capable of handling pretty high loads. So, if you look at it, this angle at which the elbow is flexed makes a difference in the effectiveness of the muscle force. So, if I were trying to hold the same load instead of at 90 degrees flexion at an angle greater than that. So, in this case for instance, then the muscle force actually gets, there is a component of the muscle force that contributes to the moment, applying the moment, and there is another component that acts along the longitudinal axis of the forearm, and that is a force that actually acts to either stabilize. So, in this case if it is flexed like this, if it is flexed greater than 90 degrees, the muscle force provides a contributing stabilizing force to the joint, it holds it together. So, that is called the stabilizing component, it is trying to push it into the cavity, the two bones together. This component is called the rotational component of the muscle force. Here the assumption we are making is that the angle of insertion is still the same, whereas in actuality you will see that as your elbow flexion changes, you can see that the angle of insertion is also going to change, okay, and we will see that in another problem. But here let us, assuming that this is always pulling in a direction which is vertical, okay, we say that, so the actual angle of insertion with the long axis of the forearm is changing, you are assuming that it stays vertical, right, in your global system. So, the muscle is always pulling in that vertical direction. So, you have this rotation. Now, if it is flexed less than the 90, then if you look at the components of the muscle force, you see that this component is now not stabilizing the joint, but it is actually dislocating, it is attempting to dislocate the joint, okay. So, it is trying to come apart, the joint is trying to come apart when this angle is lower. It is also called the dislocating or sliding component. So, basically the role of, we will call this rotational component Fm normal, because it is normal to the long axis of the forearm. We will call this component Fmt, tangential. So, role of tangential component Fmt may be stabilizing or dislocating. So, if you look at the actual the joint, you compute it as a pin joint, you compute it as a net force, we computed Fy, right, as acting downwards, compressing the joint. In actuality, it will be a distributed force because of the synovial fluid present in between the two bones. They are not in direct, no, it is not a point contact. Okay. Your Fj or sorry, your Jy is actually the resultant of this distributed force at the joint contact. So, in most synovial joints, that is what happens. If you see here, you know, it is like a fluid pressure, right. You have this fluid, it is like a lubricant in between the two bones. If you see here, it acts normal to the joint surfaces, but all the horizontal components cancel out. In this case, you have a net force along the y axis.